Welcome to Maths with AJD. We are still talking about partial differential equations, and in this video, our focus shifts to Laplace equation and boundary conditions. So, a couple of times, right from the very beginning, I've been mentioning three equations: heat, wave, and Laplace equation. And so we have also even used separation of variables to solve Laplace equation. But here, the boundary conditions attached to these Laplace equations actually determine the kind of solutions you get. And that is why this is important to consider. Okay, so let's do this. So let's start first of all with Laplace equation, just as a reminder. So Laplace equation is it's a fundamental partial differential equation that describes, it describes various physical phenomena, various physical phenomena like heat conduction. Never mind that there's also heat equation, right? Heat conduction, electrostatics, and fluid dynamics. In steady state, I think the key word here is the steady state thing. In steady state conditions, okay, it is expressed, it is expressed as nabla squared of phi equals 0. So nabla squared of phi equals 0, where phi, which is a function of x and y, is called the potential function, is the potential function, e.g., temperature. It can be temperature, it can be electric potential. If you're talking about electrostatics, it can be electric potential. Potential. So in two dimensions, in two dimensions, the equation becomes partial squared phi over partial x squared plus partial squared phi over partial y squared equals 0. So of course, if you want to extend it to three dimensions, you just add another one. Partial squared phi partial z squared equals 0. Okay, so that's what that is in two dimensions. So this becomes this equation states that the sum of the second, the sum of the second partial derivatives, the sum of the second partial derivatives of phi with respect to spatial coordinates, with respect to spatial coordinates, x and y must be 0. So Laplace equation is important, is important uh, in modeling phenomena where no external forces, because it's homogeneous, right? So it means no external forces like heat sources. So, when we talk about heat equation and we have initial condition like f of x or something, so such things don't exist here. So like heat sources or charge distributions or charge distributions are acting on the system. None of such things are acting on the system, resulting resulting in a steady state distribution. Okay. Now let's talk about general solution method. General solution method. Of course, we know already that to solve Laplace equation, which we have done in previous videos, to solve Laplace equation, you know that the boundary conditions must be specified at the domain's boundary, at the domain's boundaries. The general solution involves techniques like separation, of variables, which we have used before, Fourier series, which I also did in the previous video, Fourier series, or Green's function, which has been also used previously, but there's still a video ahead, which will be talking about Green's functions, depending, and it all depends on the geometry of the problem, depending on the problem geometry, because partial differential equations are about space and time. So the path traced by fluid flow or heat flow and everything is really important. Now, the key thing here, if you remember, the topic is about Laplace equation and boundary conditions. So the boundary conditions are really important in this situation. So we switch this over, and then I go for, say, this. Let's talk about the boundary conditions now. Boundary conditions. Boundary conditions. So, like we already know, boundary conditions describe how the potential function, phi of x comma y behaves at the boundary of the domain. So they are crucial. They are crucial for obtaining a unique solution to Laplace equation. Okay, so there are three common types of boundary conditions. Okay, if I go for this, for instance, so the first type is called the Dirichlet boundary conditions. Dirichlet boundary condition. Okay, so the Dirichlet boundary condition specifies the value of the function of the function phi at the boundary. So this deals directly with the function. Okay. And okay, still on this. And it is often used to model fixed quantities such as a fixed temperature or electrical potential or electrical potential on a boundary. So the form of that, so the form of that will be something like this. Phi of x comma y equals g of x comma y on partial omega. So if you take an example in that line, take an example, say, okay, let's say example one, right? Rectangular domain with Dirichlet condition. Okay, so consider a rectangular domain zero less than x less than a and 0 less than y less than b with the following boundary conditions. Phi of 0 comma y is equal to 0. Phi of a comma y is equal to 0. Phi of x comma 0 is 0. And of course, phi of x comma b is equal to v naught. Okay, where v naught is a constant, v naught is a constant, e.g. a fixed, e.g. a fixed voltage or temperature at the top boundary. So to solve this kind of problem solution, so we can use separation of variables like you already know. The first thing we can do is we do separation of variables, where we assume a solution of the form phi of x comma y equals x of x, y of y. Okay. Then number two, we have to substitute into Laplace equation. Substitute into Laplace equation. And what happens in that case is we have d squared. So that will be d squared x dx squared multiplied by y plus x d squared y dy squared. That is equal to 0. When we substitute that, so then the next thing is we divide That's number 3, right? Number 3, divide by x of x, y of y, and separate variables. Okay, so that's, in that case, we have 1 over x, d squared x, dy, d squared x, dx squared equals minus 1 over y, d squared y, dy squared. That's equal to lambda. So this results in 2 ODEs for x of x and y of y. So in that case, we solve the ODEs. Number 4, solve the ODEs. So we know that for x of x, the solution is xn of x equals sine n pi x over a. Then for y of y, the solution is yn of y equals sine n pi y all over a. That goes. And then we have the general solution after solving the ODEs. We talk about the general solution. Okay, so the general solution is phi of x comma y equals summation from n equals 1 to infinity, talking about superposition now, an sine n pi x over a sine n pi y all over a. That's the general solution in this situation. Then, of course, after that, we can go for 6. In 6, now we talk about the boundary condition. Apply the boundary condition. So here we have phi of x comma b equals v naught. So we do this to, so apply, this is the boundary condition. Apply this to determine the coefficients, an using Fourier series. So since we've done this kind of thing before, I'll just stop here and then we can switch over to, let this be here, and then we go for, say, this. Now, we are talking about types of boundary conditions, right? And we've made mention of the Dirichlet boundary condition. So the second type of boundary condition will be what we call the Neumann boundary condition. The Neumann boundary condition. So where the Dirichlet talks about the potential function itself, the value of the potential function. But in this case, the Neumann boundary condition specifies the derivative. So the other one talks about the function directly. Like this one specifies the derivative, which we can call the normal gradient. The normal gradient of phi at the boundary. So Dirichlet talks about the function at the boundary, but here this one specifies the derivative of the normal gradient at the boundary. So this is often used to model insulated surfaces. Insulated surfaces where the flux, the flux can be the heat itself or the electric field instead of the potential itself. Instead of the electric potential itself, the heat or electric field. You know, in the other case, it's instead of heat, we talk about the temperature, but here we talk about the flux, which is the heat instead of temperature, and electric field instead of the electric potential is fixed. It's fixed, but it is fixed, is fixed, but the potential is unknown. So the form for this, the form is, since it's gradient, right? Since it's gradient, we have partial phi, partial n equals h of x comma y on that space omega. So it's gradient in nature. So we can then consider example 2 in this case. So example 2, insulated rectangular domain. Insulated rectangular domain. So consider the same rectangular domain we considered before. The same rectangular domain. 0 less than x less than a, 0 less than y less than b, but with Neumann single M double N Neumann boundary conditions specifying that the heat flux, which is more suitable for gradient as it is here, that the heat flux at the boundaries, is 0, that is insulated boundaries. So we have partial phi, partial y of x comma 0 equals 0, partial phi, partial y of x comma b equals 0. So instead of just phi, so we have the derivatives now. So if we have this kind of situation, then we can talk about solution, right? So solution, again, we have separation of variables, where we assume a solution of the form phi of x comma y equals x of x, y of y. Then number 2, we substitute into Laplace's equation, okay, and separate variables. So that simply gives us 1 over x, the squared x, the x squared, equals minus 1 over y, the squared y, the y squared, equals lambda. So from there, we have, so under this now, we can then say that the solution for x of x is xn of x, which is cos n pi x over a since the boundary conditions require even functions. So on the other hand, we have for y of y, the solution for y of y, the solution is y n of y, which is equal to cos n pi y all over a. Okay, then we can now talk about the general solution. So 3, oh, well, I can still continue with this, right? 3, the general solution will now be pi over x comma y equals summation from n equals 0 to infinity an cos n pi y all over a, then cos n pi x all over a. So this is the general solution in this situation. So now we can go for, that'll be 3 now if you like, 3. So the constants an can be determined from initial conditions or specific heat flux values. So that goes. Now let's look at this now, and then yeah, let's use what we have already there. So this third type of boundary condition is what you call the Robin boundary condition. The Robin boundary condition, which is a mixture now. It's the mixed condition. Mixing both potential and flux together, if you like. So the Robin boundary condition is a combination. It's a combination of both Dirichlet and Neumann conditions. Where both the function value and its derivative are specified in a linear relationship. Okay. This type of condition is useful for modeling heat transfer with convection, e.g., heat loss to the surroundings. And the form of that is alpha phi, that's the potential, plus beta partial alpha partial n, as beta multiplied by the flux, equals g of xy on partial on the space, right? So, and that leads us to example 3. So example 3 is convective heat transfer. Okay, so again, consider the same rectangular domain. Consider a rectangular domain, a rectangular domain, 0 less than x, less than a, 0 less than y, less than b, with Robin boundary conditions at the top, at the top and bottom, at the top and bottom. So where we have minus k partial phi partial y of x comma 0 equals h into phi of x comma 0 minus t infinity. All right. And then we also have minus k partial phi partial y minus k partial phi partial y, okay, x comma b equals h into phi of x comma b minus t infinity. So we have this where k is thermal conductivity. K is thermal conductivity. And H is the convective heat transfer coefficient, the convective heat transfer coefficient. And T infinity is the temperature. T infinity is the temperature of the surrounding environment. Okay. So, I mean, with this, right, I'm just going to say general stuff here. So, to get the solution, I won't be explicit. I'll just give some directions as we can already, we have seen a lot of examples. So, we apply separation of variables in that case, apply separation of variables and solve the ODEs as in the previous examples. As in the previous examples. So another thing is number 2, this will lead to a solution, involving both cosine and hyperbolic terms. We already have something like that for Neumann boundary condition. So with both cosine and hyperbolic terms, similar to the Neumann and Dirichlet cases, but with additional constraints involving the convective heat transfer, Okay. All right. So it's been a lengthy one, but can we quickly look at do a comparison of these things now? Yes, I want to switch over to this and say this. Okay, this and then this. So it's a quick comparison of boundary conditions. Quick comparison of boundary conditions. So let's look at let's just do for the Dirichlet, right? Dirichlet boundary condition. So first, it specifies the value of the potential at the boundary. So it deals with the value directly at the boundary. Then another thing is that the mathematical form is phi equals g of x comma y on the space. Then next it talks about fixed temperature or voltage at boundary. Okay, that's for Dirichlet in summary. Then we have Neumann for Neumann boundary condition. Okay, so first of all, it specifies the normal derivative, which you can also call flux of phi at the boundary. So instead of talking about temperature here, you're talking about the heat flow of flux. Then the mathematical form is partial phi partial n, partial phi partial n equals h of x comma y on this on partial omega. Then the physical interpretation is about insulated surface, insulated surface where there's no flux. Then we also have the Robin. So we have Robin boundary condition. So this one actually specifies a combination. It specifies a combination of phi and its normal derivative. Okay, then the mathematical form is alpha phi plus beta partial phi partial n equals g of x comma y on the space. Then the physical interpretation is about convection heat transfer, and that talks about something mixed. That's it. So these boundary conditions form the foundation for solving Laplace equation in various physical contexts. Okay, I guess I want to write that, right? So in conclusion, right? These boundary conditions, form the foundation for solving Laplace's equation, in various physical contexts, and selecting the appropriate one, depends on the specific problem at hand, E.g., we're talking about temperature distribution. Okay. We can be talking about electric potential. electric potential. We can be talking about fluid flow. So it all depends. So that's that. Now, interestingly, I have Python code just to distinguish these three boundary conditions. So I have this code right here. Um, so here we're talking about, so here we have length in x direction, we take that to be 10. Length in y direction, we take that to be 5. We're talking about a rectangle. So it's more like we're talking about a rectangle which is 10 by 5 in nature. And then we can define our x range is 0 to 800, 0. So from 0 to where we have 100 divisions, 0 to be 100 divisions. Then we define a mesh grid for that. Then solution for boundary. So if v naught is equal to 1, which we can change this to whatever we like. Then we define the Dirichlet, the solution phi Dirichlet. We have this. Then we have the phi Neumann, we have the phi Robin, depending on how it is defined. So by the time we run this, we see the differences uh, between the three. So you see, so this is for the Dirichlet boundary condition, which talks about uh, in the something at the top. And then here you have the flux. So you have something like a flow, and then you have a mixture of the two for the Robin boundary condition. Okay. What if I change the V naught, the constant boundary value, if I change it to say 5, what does it look like? Okay, I mean it just changes the dimension, so nothing, not a big deal. Okay, there's something like this. Yeah, so here we just have what we have. So that's how that works. And with this, we come to the end of this video on Laplace equations and different boundary conditions. Let me know in the comment section how helpful this video is for you. And if you'd like me to teach on a topic or solve a particular problem, I may be able to find that time to get to do that. If you have subscribed to the channel, thank you. If you have not, please go ahead and subscribe because there's a lot to learn here. And be sure to like and share so that more people can have access to this great content we have here. Till I come your way again, keep doing maths right. Bye.